All right. So I don't know if you guys have this slide now. Okay, no. All this slide is, you might recognize it from clear back in Unit 1. It's a figure, and I believe this is correct about this edition of Petrucci. It's on page 6, figure 1.4. And basically, we're focusing on compounds over here. What you saw just a minute ago was an example of, was an example of a chemical reaction, breaking it down. It's not letting me do what I want to do. Breaking it down right here. Element broken down, compound broken down into its element via a chemical reaction. And I probably way back at the beginning of school kind of emphasized that. We did that with mercury 2 oxide a minute ago. Now this part actually I need to focus on 2 types of compounds, ionic compounds and molecular compounds. So I think I might have mentioned this clear back at the beginning of the semester, that compounds, actually there's 2 types of compounds, and we need to focus on that a little bit. All right, so what I have found helpful sometimes is to kind of have a running tally of these 2 types of compounds, because we're going to kind of compare and contrast. So we have molecular compounds, Cpd for compounds, and we'll be adding to this, and then we have ionic compounds. Okay. So, molecular compounds exist as molecules. Ionic compounds exist as formula units. So I'm going to say molecule, that's what you call them. Molecule. If you have a repeating unit of an ionic compound, I have heard it called a molecule, but more accurately, I really think it should be called a formula unit. That's its name of the repeating unit. And our marker is just not going to make it. Okay, so that's one difference between the 2, if you want to be really legitimate about it. Actually, the 2 types of compounds can readily be distinguished if you're given the formula, the chemical formula for the compound. Basically, under ionic compounds, I'm going to put metals bond with, I'll put it this way, metals, well, I'll write it out, metals bond with nonmetals. Now, when we chunked up the periodic table a while back, we said we had that jag there going kind of through the P block. And that jag actually separates the small amount of nonmetals, kind of in the upper right, nonmetals, and versus metals. Most of the stuff is metals, okay? So metals bonded with nonmetals give you ionic compounds. If you have all nonmetals, so nonmetals, I'll just put with, nonmetals with nonmetals, that means you are dealing with a molecular compound. And it's interesting because we have a lot of molecular compounds that are very near and dear to our hearts. So basically take the jag and start making compounds out of those elements. Okay? Those are molecular compounds. Okay, so now this is kind of important. The arrow thing's not as important, but it's important that for purposes of this discussion, usually, I'll say H as in the element H, usually considered or behaves as a nonmetal. Usually is nonmetal. Usually. So in all of this mess, I'm going to go ahead and draw a line under this metals right here, ionic compounds. So basically, and if you're writing up your sheet music because you're in a rehearsal and you want to make sure you look at the conductor, you always draw like a pair of spectacles. Okay, that means look up. Okay, Basically, look for the metal in your compound. Look for the metal in your compound. If you have a metal, then odds are really pretty darn good that you have an ionic compound. So these actually are molecular compounds. So these would be all cute little molecules. So let's look for the metal. I don't see any metals. And if you're like me, I guess I say that kind of casually, but just starting out, you're like, carbon, I don't remember if it's metal or not. Well, then look at your periodic table, look for the JAG, and it's a non-metal. Okay, hydrogen, I said a non-metal. Oxygen, I can't remember. I see oxygen's a non-metal. Nitrogen, I'm not sure nitrogen's a non-metal. So, you know, feel free to look at your periodic table. So I have a little video, not a lot to it. That's probably worthy of bringing up. I know there's a smoother way to do this, but okay. And I'm not going to animate this next one. Okay, we said N2H4, and this is this is NH3. I will make a little comment about specifically the compound NH3. That's ammonia. Okay, actually in lab on Thursday, we're going to be dealing with the ammonium, okay, polyatomic ion. Ammonia is NH3. It's a neutral molecule. I could animate it, and basically you just see that thing rotating. So again, you can take your hand and kind of go around all sides of it. Okay. Now I'm going to go ahead and show you these videos right quick. You know, full disclosure or whatever, what happens if you take table salt and throw it into water? And your table salt dissolves. Okay? So your table salt dissolves, and what have we been calling that? We actually have recently called that, kind of showed it kind of as a dissolving process. We'll say NaCl, solid. I'll go ahead and put water over the reaction arrow if you want to. And it forms Na plus, or Na, yeah, plus AQ. Plus Cl minus AQ. And we'll be talking more about how did I know that was an Na plus and how did I know that's Cl minus. Okay? But the point is it just dissolves and it kind of takes with it its charge. So, I think that's neat. I'm easily impressed though. So this kind of goes back to the molecules, the idea that I showed you, that animation of a hydrazine molecule. You can go ahead and kind of say those 2 nitrogens and those 4 hydrogens are part of that unit. Okay, so to me, it's not a small thing to call molecules molecules, and to call for ionic compounds a formula unit. Okay, because what is a formula unit? Well, it's a little repeating unit in an overall, if it's solid, crystalline lattice structure. For example, the sodium chloride, the way it works is if you were to identify any Na plus, it actually has 6 neighbors. It has 6 Cl minuses around it. So, like, which 2 are you going to draw, you know, for the repeating unit? Okay, it's just a formula unit. It's not as cool, I don't think, as not. Depends on how you look at it. So, I'm not sure if you have this slide. We just did this slide today. No? Okay. Just to remind you what we talked about today was that if an atom can get its electrons such that it has this NS2 NP6, and I called it an octet a minute ago. Octet, 2 plus 6 is 8. Okay, if it can actually get that configuration, then it's really a happy thing. And if it's bonding with another atom, it can actually either lose or gain electrons, or it can share electrons to get that complete octet. All right. So starting with, let's see. There's 2 types of bonds. And actually, I've already said this. Covalent bonds actually come about when electrons are shared. Okay? They don't have to be shared equally, but at least they're shared. We'll talk about that kind of unequal sharing in a minute. Ionic chemical bonds come about, and it's almost stepwise to me. An electron is first transferred, and then the ionic bond is formed. So ionic bonds form after an electron is transferred. You end up with the thing that gives up an electron is positively charged. The thing that takes in an electron is negatively charged. So then you kind of have this, it's literally an electrostatic sort of, okay, because the positive and negative create that ionic bond, chemical bond. So something to add then, ionic compound, it contains at least one ionic bond somewhere. I like the words at least one. At least one ionic bond. And under ionic bond, I'm going to go ahead and say electrons transferred. Ionic bond, E transferred. If we compare that to a molecular compounds, okay, molecular compounds contain only, or their atoms are connected only by, contain only covalent bonds. And under covalent bonds, I'm going to put E shared, electron shared. And then up here, where I call this whole column molecular compound, I'm going to call it, the synonym for molecular compound is covalent compound. Covalent Cpd, same diff. Actually, I don't know, it's just in the course of this afternoon, I've kind of lapsed back and forth. I didn't mean to, but I might have. Okay, so molecular compound, covalent compound, the same. Molecular compound contains only covalent bonds. And I kind of think of it like if you have, and it's quite possible that you have kind of a complicated molecule. You have a kind of a complicated compound with lots of chemical bonds. If you have only one ionic bond, it's contaminated. It's an ionic compound. Okay. All right. Tug of war at the top. If you want to put tug of war, that's exactly what this is. This is a tug of war. Okay. So in chemical, the electronegativity deals with only one pair of atoms. I think that's the way I think of it. We have atom A, okay, joined to atom B. Okay. The electronegativity of either atom is basically how much they want to tug electrons to themselves. So I'm going to go ahead and say, put an arrow there, tugging electrons to A, okay? And I'm going to actually call that, that'll work. I'm going to call that electronegativity. Now, we use this symbol. The word electronegativity, I never thought of it until just now, but it's a long word. If you had to write electronegativity, and I suppose some people may abbreviate it EN, I'm not sure, but we use the Greek letter chi, so it's like a fancy X. Okay, so that would be electronegativity of A, okay, and here, this would be the electronegativity of B, the atom itself. A pair of atoms bonded together, okay. So, remember a minute ago, I said I said metals tend to go, whoop, you can have my electron. Sodium, whoop, you can have my electron. Metals tend to have what we call low electronegativities. Non-metals tend to say, I want more electrons. So non-metals have high chi, have high electronegativity values. So one of the trends you're going to want, and this will help with your Lewis structures. Actually, when we draw your Lewis structures in a couple of weeks, you're going to have to be faced with a couple of different atoms and know which one has the lowest electronegativity. So we have this trend in electronegativity for the group A elements, okay, for the main group elements. So basically take out the B's, take your 2 columns and your 6 columns and squish them together. Okay, and this is the trend. Electronegativity increases across the period, and electronegativity in the same group increases from the bottom up. So sometimes actually, this purple arrow over here, I'll have it over here. So it increases this way, increases this way. Okay, so with that said, we'll go ahead and, see that the group 8A, those are your rare gases. Those actually are your inert gases. Their electronegativity doesn't make sense because they don't like to bond with things. Okay, so starting with fluorine, actually fluorine is your highest electronegativity. Okay, that's kind of how that works. So I have a couple of things to show you with regard to electronegativities. Now, you're going to want to sometimes actually pull off a value of a chi value, electronegativity value. This wouldn't be very helpful, okay, but this would. The electronegativity values are sometimes called the Pauling values. So Linus Pauling actually won a Nobel Prize in chemistry. I don't know if it was for this or something else. But these are basically, the higher their electronegativity, the more that an atom wants to hoard electrons to itself. So you can kind of see what I said just a minute ago. Fluorine, okay, top of the mountain. Okay, over here, cesium, francium, low electronegativities. Okay, so let's see how that translates to something meaningful between a couple of atoms. So I printed this off, but then I forgot and left it on the printer. But you guys have these values, and we're going to refer to them in a minute. So when you guys came up with temperature differences, when you came up with enthalpy differences, okay, you came up with temperature differences, we called that a delta T, did we not? Okay, I think we did. When you came up with enthalpy differences, we call that delta H, okay? So actually, now I have something called a delta chi, electronegativity differences. So the way you I don't have this in my notes anywhere, but delta chi, you can calculate it. If you have two atoms that are joined together, you take the value of A, the Pauling value, the electronegativity value of A. From that, you subtract the electronegativity value of B. And I think we've run into these lines before. That means, of course, absolute value. So we're looking at the absolute value of the difference between electronegativity difference. So here, when it says if you have a large electronegativity difference, then actually electrons are going to be transferred. I'll go ahead and say transferred from, maybe already this makes sense, from low electronegativity value to high. A small difference in electronegativity, and then actually electrons are going to be shared. And to me, it's like the tug-of-war thing going on, okay? So it's all about tug-of-war. So just for kicks, let's go ahead and look at the couple of different things. Under molecular compounds, I'm going to put examples H2O. And under ionic compounds, I'm going to put examples NaCl. So let's go ahead and execute this. So if I have an oxygen, bond, two hydrogens, okay? When we're looking at the electronegativity difference, we basically have to isolate one chemical bond. So I'm just going to pick the left one. It really doesn't matter. So we can describe the nature of that chemical bond or evaluate the nature of that chemical